Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. CompTIA recommends that Security Plus test takers have at least 2 years of experience. Even with that being the case, we're going to review the required networking knowledge that you need for the exam. Now, before we dive in, you have to be familiar with how the OSI model and the TCP/IP model operate. A protocol defines the rules of how computers communicate with each other. For example, TCP and IP are core to providing basic connectivity, where POP3 handles email traffic. We're going to cover some basic networking protocols that you need to be aware of. TCP, or the Transmission Control Protocol, provides connection-oriented traffic, and it guarantees that traffic is delivered. TCP uses something called the three-way handshake, where the client initiates a connection by sending a SYN or a synchronized packet. The server then sends back a SYN-ACK or a synchronized acknowledge packet, and then the client sends an acknowledge or an ACK packet to complete that three-way handshake and establish the connection. On the other hand, UDP, or the User Datagram Protocol, provides connectionless sessions, meaning that there's no three-way handshake. UDP uses its best effort to deliver the traffic, and we also refer to this as fire and forget, because unlike TCP traffic, UDP is not going to verify that the traffic's been delivered. IP, or the Internet Protocol, is what we use to identify hosts on a network with their IP address, and it's used in delivering traffic between different hosts. IPv4, or IPv version 4, uses 32-bit addresses in dotted decimal format, so like 192.1.1.10. IPv4 has been the traditional addressing that we've used. However, given the rapid expansion of internet-connected devices, the available addresses are running out, and that's where IPv6 comes into play. IP version 6 uses 128-bit addresses using hexadecimal code. There are significantly more IPv6 addresses available for use, in addition to some of the other features that IPv6 allows. ICMP, or the Internet Control Message Protocol, is used for testing connectivity with tools like ping and traceroute. Interestingly enough, we might have ICMP blocked on a lot of devices and systems because it's frequently used in attacks and mapping out a network by attackers. The Address Resolution Protocol, or ARP, takes IPv4 addresses and resolves them to Media Access Control, or MAC addresses. MAC addresses are the physical hardware address of your network interface card and are used at layer 2 of the OSI model to deliver traffic to systems. An important point to make about protocols is that all protocols aren't enabled right out of the box. As we identify business needs, we can start to enable the required protocols. Likewise, if we identify that we no longer need a protocol or we're no longer using it, we should disable it for improved security. Over the last several years, voice and video have switched in many cases to network-based traffic. These protocols tend to use UDP instead of TCP protocols. One important protocol is Real-Time Transport Protocol, or RTP, and that's a common protocol used to deliver audio and video over networks. Another important protocol is the Secure Real-Time Transport Protocol, or SRTP, which allows us to encrypt the traffic and to provide message authentication and integrity for RTP. Since we're sending our video and audio over the network, this can all be used in something called a replay attack, where an attacker tries to reuse or modify that conversation. Session Initiation Protocol, or SIP, is another protocol that you need to know about, and it's used to initiate, maintain, and terminate voice, video, and messaging sessions. Once a session is formed, either RTP or SRTP take over. An important point regarding SIP is that there are clear text messages exchanged that could reveal metadata like software on the phone equipment. Transferring data across a network is commonplace in every organization. With that being said, some protocols are much more secure than others. FTP, or File Transfer Protocol, is commonly used for uploading and downloading data to an FTP server. Now, there's two FTP modes that you need to know about. First, we have FTP Active Mode, which operates on TCP port 21 for control signals and TCP port 20 for data. And then we have FTP Passive Mode, or PASV, which uses TCP port 21 for control signals and a random TCP port for data. Typically, we want to have passive mode disabled so we aren't allowing random ports to communicate. TFTP, or Trivial File Transfer Protocol, uses UDP port 69, and it allows for small data transfers. You might have used TFTP to upload data to network appliances in the past. However, we typically don't need or allow TFTP on our networks. Secure Shell or SSH works on TCP port 22 and forms an encrypted communication session. Over that session, we can use FTP or Secure Copy (SCP) to transfer data securely. SSL or Secure Sockets Layer is most well known for protecting web or HTTP traffic in the browser, turning it into HTTPS. TLS or Transport Layer Security is the replacement for SSL, but essentially it serves the same purpose. IPsec or Internet Protocol Security is used to encrypt IP traffic. IPsec is most commonly associated with VPNs or virtual private networks, and it creates a tunnel between two systems. SFTP or Secure File Transfer Protocol uses TCP port 22 and allows for FTP traffic to be encrypted over SSH. FTPS or File Transfer Protocol Secure uses TLS to encrypt FTP traffic. FTPS might use TCP ports 989 and 990 or 20 and 21. Email and internet or web access are very common in almost every organization today. Think about how often you use these on a daily basis. Email protocols that you need to know about include SMTP, or the Simple Mail Transfer Protocol, which is used to transfer email between SMTP servers and clients. SMTP uses TCP port 25 for unencrypted email and TCP port 587 for email that's encrypted using TLS. POP3 and Secure POP, which is Post Office Protocol version 3, is another email protocol that you might be familiar with, and it uses TCP port 110 for unencrypted email and TCP port 995 for encrypted communications. IMAP4 and Secure IMAP, which is the Internet Message Access Protocol version 4, is the last email protocol that you need to be aware of, and it allows users to manage their email in folders on the email server. As an example, with IMAP4, if you were to mark an email as read or move it into another folder on your cell phone, this change would sync with your server. IMAP4 uses TCP port 143 for unencrypted connections and TCP port 993 for encrypted connections. Web protocols that you need to know about include HTTP, which is the Hypertext Transfer Protocol, and that's the standard protocol for web traffic and internet traffic. HTTP uses HTML or Hypertext Markup Language to display web pages, and HTTP operates on TCP port 80. HTTPS is the same HTTP traffic over SSL or TLS, which means the traffic is encrypted while it's in transit. HTTPS uses TCP port 443. A few indicators besides the port that also help to identify encrypted traffic include a padlock icon next to the URL and HTTPS in the web address. If you go to a shopping website or somewhere where you provide credentials, you should always be seeing HTTPS in the URL address bar. Within enterprise networks, you will always find some type of directory service used to manage user accounts and identities. Most commonly, you're going to see Microsoft Active Directory Domain Services, or ADDS. Lightweight Directory Access Protocol, or LDAP, is a protocol that's used to query directory services like Active Directory using TCP port 389, or if we use LDAP Secure, LDAPS, then we're going to use TCP port 636 to encrypt data with TLS. It would be impossible and impractical for people, especially our administrators, to physically access all of our network systems. Remote Desktop Protocol, or RDP, allows users to connect directly into systems without physically being in front of that system. RDP uses TCP port 3389 or UDP port 3389. From a security standpoint, you should never be able to remotely log into a system from outside of the network unless you've connected internally first through a VPN or a virtual private network. Remote access directly from the internet is very dangerous, and it's asking for hackers to attack us. OpenSSH is used to securely connect to remote systems using SSH. On the screen, I've included some common commands. So the first one, SSH, and then the server name, will just try to SSH into that server, and it will ask you for a username and password. The next command, you can do SSH, provide the username and the server IP address or the server name, and then it's going to ask you for your password. If you want to create SSH keys, which is a little bit more secure, then you can use the commands at the bottom of the screen, where you first have to generate a key, and then you actually have to copy the public key over to that remote server. One of the protocols that we don't always think about, unless it's off, is our clocks. It's important to keep our system clocks synced because some protocols require it, and also from a security standpoint, if we have accurate clocks, then we can completely recreate that timeline of events that have happened. Network Time Protocol, or NTP, allows us to synchronize time within tens of milliseconds. Every computer on your network needs an IP address, but should we manually assign these addresses? Dynamic Host Configuration Protocol, or DHCP, allows us to dynamically assign IP addresses to hosts, although we might want to actually manually assign IP addresses to our servers for various reasons. IPv4 is the first version that we've used for IP addressing. With this, we use 32-bit addresses in decimal form, so 10.10.10.10. Each octet, so where each number is 8 bits long. There's two different types of IP addresses that you need to know about. There's public and there's private. Public IP addresses are controlled, so we have to purchase them or rent them from an internet service provider. Private IP addresses aren't routed across the internet, and we don't have to rent or purchase these. You can see on the screen here that we have Class A, Class B, and Class C private IP addresses. IP version 6 was created because we're running out of IPv4 addresses to use. IPv6 has 128-bit IP addresses in a hexadecimal format. You can see on the screen the IPv6 example address is really long. Each hexadecimal character in it is composed of 4 bits. IPv6 uses unique local addresses that start with FC00 and they aren't assigned to systems on the internet. If you've ever connected a computer into a network, you probably realize that you're automatically given an IP address through a protocol called DHCP, or Dynamic Host Configuration Protocol. DHCP servers are responsible for assigning IP addresses, but a problem exists if unauthorized servers can be introduced. DHCP snooping prevents unauthorized DHCP servers, also called rogue DHCP servers, by allowing us to identify trusted ports on a switch so that DHCP traffic is only accepted from those ports. For example, if we have our DHCP server plugged into port 1 of our switch, somebody can't plug in another DHCP server into port 2. This is really important because if DHCP information like DNS servers or IP network information is modified by an attacker, then they can intercept traffic and do all kinds of bad things. Domain name system, or DNS, is a protocol used to resolve host names to IP addresses. A good example of DNS at work is if you try to visit a web page, your computer is going to ask for the IP address of the domain name. Then the DNS server is going to return the IP address so that you can route traffic to the correct location. On the screen, you can see different types of DNS records that exist. Nslookup, or name server lookup, is a command used to troubleshoot DNS problems. Specifically, you can determine if a DNS server can resolve host names or fully qualified domain names. DIG replaces Nslookup on Linux-based systems and has the same functionality. Since DNS provides a location where to send traffic, attackers are extremely interested in modifying entries. DNS poisoning, or DNS cache poisoning, is when an attacker can modify the DNS cache with a bogus IP address. What if you were trying to go to facebook.com, but instead you were sent to an attacker's webpage? That'd be bad news. Domain Name System Security Extensions, or DNSSEC, is a suite of extensions to DNS that provides validation for DNS responses by adding a digital signature known as a resource record signature, or an RRSIG. Quality of service, or QoS, allows administrators to prioritize traffic on the network. For example, you can prioritize streaming traffic if you host a YouTube streaming show. Two types of messages that you need to know about when it comes to network traffic are unicast, meaning one-to-one traffic, where traffic is sent directly to a destination IP address. And then we have broadcast messages, meaning one-to-all traffic, where a host sends traffic to all the other hosts on a subnet. Let's talk about some of the most important and most common devices that you're likely to run across in your career. Switches are devices that operate at layer 2 of the OSI model, and sometimes layer 3 with the right equipment, that have systems physically connected and intelligently transfer data. Let's first talk about how a switch works if it doesn't know about any devices. First, computer 1 sends traffic to computer 2, including the MAC address of computer 2. Since the switch doesn't know where computer 2's at, it's going to forward traffic out of all the ports. At this point, the switch is going to store the MAC address from computer 1 that it just learned about in case it needs it for later. Computer 2 is going to hear this and respond back to computer 1 with its MAC address, and then the switch is actually going to store the MAC address for computer 2 in its memory for later use. Now that you know how switch works, you might be sitting there wondering what some of the security benefits of a switch are, so let's talk about that now. Prior to switches, there was a device called a hub that would always send traffic out of all of its ports. Unfortunately, attackers could intercept traffic on a hub and see everything happening. With switches, traffic is intelligently transported to the correct systems, so if an attacker is plugged into port 3 of a switch, they won't be able to see the traffic between ports 1 and 4. Port security is a protection that can limit the amount of computers that are connected to ports on a switch. With port security, we can simply shut down ports that shouldn't be in use. We can also use MAC filtering, which only allows specific MAC addresses to plug into ports on a switch. A good example of port security is if we only want to allow a single host to connect to a port, somebody couldn't bring in a wireless router from their house to plug in multiple devices, thereby extending that port. One of the potential problems with a switch is something called a broadcast storm. Broadcast storms, which are also called switching loops, are where we have multiple switches connected to each other and they're constantly sending out broadcast messages through all their ports. This eventually leads to using all the processing power in the switch and effectively disabling it. Spanning Tree Protocol, or STP, is a feature that's available on most switches today. It intelligently disables certain ports in our broadcast storm example and prevents the issue from occurring. Rapid STP, or RSTP, is the newer version of the STP feature. Bridge Protocol Data Unit, or BPDU messages, are used by switches to detect loops, and they're sent out of non-edge ports, which basically means ports that don't have computers, printers, or servers connected to them. Unfortunately, switches can't automatically detect an edge port versus a non-edge port, so technically if we don't have protections in place, then a user could plug in a switch instead of their computer and start sending BPDU messages. A feature that we can use to prevent this is something called BPDU Guard. With BPDU Guard, we can identify non-edge ports where we expect BPDU messages to be sent and then disable other ports that detect BPDU messages. Routers are network devices that connect multiple network segments so that we can route traffic between them. Routers don't pass on broadcast messages, and so each segment connected is considered its own broadcast domain. You might see software that allows routing capabilities, but typically the best and most reliable option is a physical router like those from Cisco. Access control lists, or ACLs, are a list of rules that we configure on routers and firewalls to either permit or deny traffic. We call this rule-based management because each entry is like a rule that's read from the top of the list to the bottom. ACLs can be helpful in providing security, but they're fairly basic. Some of the things that we can do with ACLs include filtering by IP addresses and networks, ports, and protocol numbers. ACLs also have something called implicit deny, which means that if there isn't an entry to allow certain traffic, it's going to be denied by default. I wouldn't suggest creating a rule to allow all traffic to bypass the implicit deny because it creates a security issue. On the command line for Windows and Linux computers, you can use the command route print to see all the paths known by the computer. If the computer doesn't know about a route, it's going to use the default gateway. If you want to add a route to the computer, you can use the route add command. This is also an interesting set of commands because attackers do occasionally add new routes so they can intercept traffic, so we can also verify what's shown. Firewalls are in network compliance with the main purpose of filtering incoming and outgoing traffic for specific hosts or entire networks. Just like a firewall in a car, these types of firewalls protect our internal networks. The simplest implementation of a firewall will have access control lists, just like a router, and they also have an implicit deny rule at the end of the list. Host-based firewalls monitor traffic on a single host like an individual computer or a server. Many operating systems today have a built-in host-based firewall included, but there are third-party options that exist. In an enterprise network, host-based firewalls are one of the last chance defenses that we have, but if you have employees with mobile devices like laptops, then host-based firewalls might be the one and only defense when connecting to a public Wi-Fi network. Firewalls come in both software and physical hardware options, with each having its own pros and cons. Depending on what you're trying to accomplish and where you want to deploy the firewall, that's going to impact which option you choose. For example, a physical network-based firewall is frequently used to protect servers and protect the entire network. Stateless firewalls are the simplest form of a firewall, and they use access control lists to identify allowed and block traffic. Firewall rules typically are going to have permission, so is the traffic permitted, meaning is it allowed, or is it denied, meaning that it should be blocked. The protocol, is it TCP or UDP? Source, so the source IP address. The destination IP address. And the port or protocol, so 443 or HTTPS, depending on what the firewall supports. Stateful firewalls inspect traffic at a deeper level and make decisions based on the traffic context or state. For example, if a stateful firewall sees an acknowledgement message, which is the second step of a three-way handshake for TCP connections, but it never saw that first message or the send message, then the firewall can block that traffic intelligently. Web application firewalls, or WAFs, are specifically designed to protect web applications. For example, if you have a web application that takes user input, the WAF could detect potential attacks like cross-site scripting or XSS and block them. Next generation firewalls, or NGFWs, are even more advanced firewalls than what we've talked about so far. These firewalls can perform deep packet inspection and look at traffic all the way to the application layer of the OSI model. This is especially useful because now we can start to detect malicious protocols and traffic potentially embedded in seemingly normal traffic. Network designs require large amounts of thought and understanding of how things work and where things are located. Two major zones that we have in our networks include the intranet, which is our internal network where our users and our servers sit. Then we have our extranet, which is the part of the network that can be accessed by those outside of our internal network, like business partners, customers, or vendors. Screen subnets, which we also call demilitarized zones, or DMZs, are a potential third area of our network, and that serves as a buffered zone between a private network and the internet. We'll have some protections in place for the DMZ, but these areas are accessible to the internet. That way employees can access services like their email. NAT, or Network Address Translation, is the protocol that we use to translate public IP addresses to private IP addresses and private IP addresses back to public addresses. Network Address Translation gateways are the server or appliance that's providing the private IP addresses and the path to the internet. NAT allows public IP addresses to be conserved instead of having one for every single device on your network, which would be expensive because you have to purchase or lease them. NAT also allows us to hide or obscure devices on our internal network. PAT, or Port Address Translation, is a common form of NAT that uses ports to track where traffic should return to. NAT can either be static, which means that it uses a single public IP address and is a one-to-one mapping. This means one private IP address with a single public IP address. Or we can use dynamic NAT, which uses multiple public IP addresses in a one-to-many mapping. Essentially, dynamic NAT can load balance traffic across multiple public IP addresses. Physical isolation, or air gaps, are a measure used in high security areas like classified or industrial system facilities, and it means that the networks aren't physically connected to any other network. This can drastically reduce the risk to the system, but of course it creates additional workload for performing things like updating antivirus definitions or patching without being connected to the internet. As we've been discussing, devices like routers and firewalls help us to separate and segment traffic between networks using access control lists. There are lots of reasons why we either don't want parts of our network to talk to each other or possibly only communicate one way. Virtual Local Area Networks, or VLANs, are a technology that allows us to logically break up a switch into different groups. For example, we might have ports 1 through 10 in the finance VLAN and ports 11 through 20 in the sales VLAN. We might even separate out our voice over IP traffic or our VoIP traffic for our telephones from the internet browsing traffic. VLANs allow us to further add security and isolate traffic from each other. Zero Trust is a hot topic over the last several years, and essentially it means that every action performed has to be verified. Traditionally, we focused a lot on perimeter defenses like firewalls, but once you were inside of a network, then everything was trusted because it's secure, right? Well, unfortunately, that makes things a lot easier for attackers. So with Zero Trust, it assumes that the attacker's already inside the network and it provides further protection. Systems dedicated to a specific need are called network appliances. Now we're going to talk about some very specific appliances that you may or may not have heard of before. Proxy servers, which sometimes we also call forward proxy servers, are used to forward requests for clients like web traffic. Proxy servers can improve performance by caching content so less users have to make the same request to the internet, but they also allow content filtering like specific types of websites. This also means that your proxy server could slow down traffic if it doesn't have the appropriate system resources. Transparent proxies will accept and forward requests without modifying them. Think of using these for caching content. Non-transparent proxies can modify or filter requests. Think of using URL filters to prevent certain websites. We can get URL filter lists from third-party companies to protect our network. And then reverse proxies accept requests from the internet, typically from a web server. Essentially, web clients are reaching out to the reverse proxy that behind the scenes reaches out to the real web server. Reverse proxies can serve as a load balancer for external internet traffic. Unified Threat Management, or UTM, is a single security solution that provides multiple controls. The idea with UTM solutions is that they simplify the administration of security with a single solution instead of having multiple devices. Potential UTM features might include URL filtering, malware inspection, content inspection, and DDoS mitigators. Jump servers or jump boxes are a hardened system that requires somebody to connect to it first before reaching a certain part of the network. For example, you might have a user that needs to SSH into a jump server before connecting to a database server, which only allows connections from that jump box. On the screen, you can see a sample command to use a jump box. With the growing popularity of IPv6, it's important that you ensure your security controls and systems can adequately protect against security vulnerabilities. Not everything today is going to provide security for IPv6, and that's why many companies are still using IPv4.